You have fallen into Event Horizon with John Michael Godier. In today's episode, John is joined by Dr. Samuel Courville. Dr. Samuel Courville is a planetary scientist whose work explores the geologic and hydrologic evolution of small worlds across the solar system. At the Planetary Science Institute, he investigates subsurface water processes, cryovolcanism, and the long-term potential for habitability on worlds once thought geologically dead. His research has revealed that Ceres, the large object in the asteroid belt, may host evidence of recent hydrothermal activity and a persistent subsurface brine reservoir, suggesting internal energy sources that could sustain habitable environments far longer than expected.
Dr. Samuel Courville, welcome to the program.
Thanks so much for inviting me.
Now, Doctor, you have an extraordinary idea. As somebody that has been interested in the question of are we alone, or is life on Earth alone, perhaps more accurately, for over 40 years, I have to hand it to you because in that time, we've had two potential ways where microbial life could survive, environments in the universe that could survive. And one of these obviously are terrestrial worlds like Earth and Mars in the past, and maybe even Venus in the past, but also ice shell moons. However, it has now come on the table that asteroids, or perhaps minor planets, depending on what definition you use, but I'll call Ceres an asteroid, just because I like to, because it's in the asteroid belt and it's the largest one. But it is also a very weird one, and it's turned out far weirder than anybody ever envisioned because it seems to have salty, briny water moving around inside of it and the conditions and chemicals for life. Tell us about your research regarding Ceres.
Yeah, well, it's funny that you call it an asteroid. It was the first discovered asteroid just because it's the largest object in the asteroid belt. But I think nowadays we'd really call it more like a dwarf planet. When you look at it compared to the other asteroids, I mean, it's a significant fraction. It's like a third of the mass of the asteroid belt itself, and it's almost a sphere. It's really closer to things like dwarf planets, like the icy moons in the outer solar system, than it is to asteroids. But it's a little bit difficult to appreciate how special Ceres is just from like looking at it in images. It kind of looks like a gray space rock, like a lot of the other things in the asteroid belt. But by mass, it just has so much more water and organic matter than Earth, for example. And by organic matter, I'm just referring to large carbon molecules. So you can look at the composition of Ceres, and though it looks like a dead rock today, and of course there's no evidence that life is on Ceres right now, but if you try to track what its conditions may have been like in the past, you may have had a body that was more similar to some of those icy moons in the outer solar system that we're talking about with subsurface liquid water environments.
So it might have looked closer to something like Enceladus in its past. Is that correct?
You could say like its interior might have, because of course Enceladus right now has all this like tidal warping. It's being pushed and squeezed by Saturn, whereas Ceres has probably been sitting out there alone for most of its existence. So it doesn't have any of these complicated present day stresses and heating that could be keeping it super active, geologically active. But in the past, it may have had more heat. And so what I mean by that is there are radioactive isotopes. So this is a way many planetary bodies generate heat over time. Radioactive isotopes like potassium-40 generate decay heat as they decay into stable isotopes. And some of these are longer lived. Potassium-40 has a half-life of like 1.4 billion years. And so as it decays slowly, it just slowly generates heat. And so it can generate heat over time, keeping the interiors of these bodies warm, these planetary bodies warm. So in the case of Ceres, for example, that heating would sort of peak a couple billion years ago. And so right now it's cooling on the interior, but it could have been warmer a couple billion years ago. That means its interior could have had liquid water environment. There may still be some briny liquid in the interior. We don't know for sure. We don't know the current state of the temperature within Ceres. We don't really know how hot it got in the interior either. My recent research is hypothesizing, it's creating a model based on what we know about Ceres composition and size of what the temperature could have reached in the interior and what that means for the liquid water environment and for possible life.
Now, what of being helped along with chemistry? In other words, could you have a chemical process going on, carbon dioxide, methane interacting, things like that are going on that are making it a special case where it might actually be warmer than what radioactive decay could have done?
Yeah, so the key piece here. So let's first take a step back, right? Why do we care about these aqueous environments within these bodies, right? We care about the ocean worlds in the outer solar system because we think they have subsurface liquid water environments. We think those could be habitable for microbial life, right? What does microbial life need? It needs liquid water. It needs the right environmental conditions. It can't be too cold, can't be too hot, can't be too acidic, can't be too basic. If we go by what we know about life on Earth, if we limit life based on all the constraints that life follows here on Earth, there's two other ingredients that life might need. There's two other ingredients. One, it needs for sure, it needs energy. We're very familiar with this concept, right? We need to eat food to survive. We're extracting chemical energy by eating food. So there has to be disequilibrated chemistry in the environment that a microbe could take advantage of by bringing two different molecules that are at disequilibrium into equilibrium. They can extract energy. And the last is time. The last ingredient that life may need is time. We don't really know how life arises. We don't know how important time is for this process, but likely we need a lot of time for the right ingredients to come together. So what that means is we need an environment that's geologically stable, so the conditions are staying relatively similar throughout millions, billions of years. So what this decay heat could do for Ceres is provide a long-term source of stable heating and chemical disequilibrium, a source of food and time for life to arise within an aqueous environment in Ceres' subsurface. And so when I talk about this chemical energy, where carbon dioxide and methane come into play here, is carbon dioxide and methane are potential energy sources for a microbe. Methanogenesis, microbes can take advantage of converting CO2 to methane to extract energy to survive. That's one possible metabolic pathway that microbes can take advantage of. If you heat the rocks that we think would make up the interior of Ceres, as you heat it, you can sort of imagine you're like baking the rocks in the interior. And as you bake those rocks, you're going to release some fluids and gases, some of which are going to be CO2. And so if the ocean, I'm going to say ocean here, if Ceres had a subsurface ocean or a briny liquid layer in the subsurface, but in between the icy crust of Ceres and the rocky interior, the gases and the volatiles that are baked out of the rocky interior, the carbon dioxide, the water that is baked out and released upwards from the rocky core can mix with the rest of the fluid in the shallower subsurface. And that's where a microbe could possibly take advantage of this chemical energy and survive. So that's the crux of my recent research.
So follow the water has been the idea for a long time now. You know, you're looking for liquid waters. It's solvent of life, and there's not a whole lot of other liquids other than maybe ammonia that are common in the universe.
That's not such a nice liquid.
Yeah, ammonia, not so much. Water's beautiful, though, and chemistry happens within it. We see that, and it's happening within our our bodies right now. However, follow the water. But I'm going to ask a different question. Follow the salt. As Ceres has. Hold on a second. I have a police car passing by. Hosting a podcast from an urban area is sometimes follow the salt. Ceres has mysterious white patches, and indeed, so does Mars. Sometimes when a rover digs something up, mysterious white patches that are attributed to salts. And Earth's ocean obviously is very salty, briny, and we're looking at brines here. Do those salt deposits represent evidence of briny liquid water somehow making to the surface of Ceres?
They most certainly indicate some briny liquid. The bright spots on Ceres, probably the most fascinating part about the planet, right? So you can look at these bright spots there within, perhaps the most famous one, within Akator crater. You can look at it and you see, oh, it's in the crater. And the question is, well, when that impact occurred, maybe it weakened the structure of the crust a little bit. And so now this water, that's this briny liquid that's in the interior of Ceres, now has a pathway through fractures to make it to the surface. Then, of course, it makes it to the surface, and water isn't stable on the surface of Ceres. It's going to evaporate. So it evaporates all the way and leaves behind salts and evaporate minerals like carbonates. And so the question is, did this liquid come from a briny layer within Ceres' interior? Is that briny layer still there today? We think it is because the evaporite deposits themselves aren't all that old. They're perhaps tens of millions of years old instead of, the 4 billion years plus that Ceres is itself. So the question is, are these evaporite deposits from liquid within the interior of Ceres?
Now, differentiation. And we know from the meteorite collections that asteroid parent bodies, the original ones, were large enough to differentiate. You end up with things like iron meteorites from cores. Then you have palladides from the sort of transition zone to a mantle. And then you've got chondrites and all that stuff. But given the size of Ceres, it seems to be its own parent body. In other words, it's not a chunk of something, as far as I'm aware. Do correct me if I'm wrong on that. So is it a preserved, almost planetesimal body that just managed to not get hit by anything huge enough to shatter it into a bunch of meteorites? But does that make it unique as far as life potential in the solar system? In other words, are there any other asteroids? We haven't reclassed the rest of them as minor planets yet. Well, are there any others that could be doing this? I mean, some of them look wildly volcanic. Like, for example, I can't remember the name of the asteroid, but it's a source of eucrites, which are clearly basaltic. So what is different about Ceres from the rest of the asteroids?
Yeah, so I mean, you're really hitting at, I think, my favorite aspect of Ceres is because I do think it is a relatively early solar system. I think it is one of those planetesimals, one of these bodies that formed in the early solar system and has managed to survive without too much going on. It's a great record of the most fundamental planetesimal formation processes. So Ceres itself looks like other C-type asteroids. Its composition is probably somewhat similar to carbonaceous chondrite meteorites. Yes, you could probably call it its own parent body. I don't believe we have any reason to believe that any of our samples, our meteorite samples, are from Ceres, though I could be wrong on that. So these are special meteorites because these are the carbonaceous chondrites. These are the meteorites that have relatively high abundances of carbon in them, and they also appear to, in many cases, have extensive aqueous alteration. So these meteorites we have, these carbonaceous chondrites, are preserving records of aqueous processes with organic matter. So Ceres might just be a great lab for investigating how this material forms, comes together, undergoes geological processes in the early solar system. And then what happens to it without it being disrupted by impacts and other catastrophic processes. There are other asteroids, none quite as, exceptionally, none other rise to the level of dwarf planet status like Ceres does. But that's where I want to come back to. Perhaps Ceres is more like these other icy moons that we have in the outer solar system. The outer solar system has the moons of Saturn, Uranus. Some of these moons are similar in size to Ceres and have similar bulk densities and are similarly, spherical. And so you can get bogged down in the classification of objects, but the geological processes, the materials that accrete together, the compositions that come together, what happens when you heat them, what happens when they undergo the pressures that they do. These are relatively small bodies. The pressures aren't extreme. The aqueous processes, what happens when the water ice that they accreted with melts and interacts. These processes are all likely similar on all these different bodies, and we can talk about some of the other bodies later if you'd like. When we talk about differentiation on Ceres, so we can kind of, there's multiple different levels. You can talk about, and it's all a function of heating. So first we form a body, right? We form a planet, we form a planetesimal. Well, we first form a planetesimal, and those planetesimals are accreting together the material that's available in that primordial protoplanetary disk. A body like Ceres probably formed with some rocky material and some ices. So the first step as the interior of Ceres heat is going to be to melt the ice. And that's where we're going to create the first aqueous environment. But most likely this happened pretty early in the history of the solar system, the first few million years. And that comes from our measurements of carbonaceous chondrite meteorites. We can see when we think those meteorites underwent aqueous alteration, when the minerals in the rocks were altered by the liquid water. So likely Ceres had that aqueous alteration early in its history. Now, if it continues heating, that's when we can start sort of baking the rocks in the interior. And so we can take the minerals that would have been hydrated, altered from the liquid water, and start baking them, getting them hotter, and then we can have them release their volatiles again. Now, this is probably where, if Ceres even got that warm, that may be where Ceres thermal evolution stopped. If it got much hotter, then you would end up things like melting the rock. And that's where you can end up with these more conventional volcanic worlds like you were talking about, where you can actually melt rock. You can end up with volcanism. You can end up with metal cores in their interior, where the rock differentiates from the metal once it melts. But we don't think Ceres reached that level of thermal processing in its interior.
The early solar system must have been quite a place with millions of Ceres-sized objects floating around, all doing this. And a lot of them obviously just got cleared away, late heavy bombardment and all that stuff. And then you have the comets, which the line between an asteroid and a comet is somewhat thin. But still, do you think, however, that with the conditions of abiogenesis being what we think they are, with the water and the heat and the energy sources and food and all of that, nutrients, organic chemistry, do you think that this solar system could have been spawning microbes very early on? And again, the time factor that you mentioned, but say that it doesn't take very much time, because it doesn't appear to have taken Earth very much time. The very first moment it possibly could have seen abiogenesis, it did. But do you think that was happening everywhere? Do you think that this environment was common based on the water-altered carbonaceous chondrites and everything else that we see? Do you think that this was a much more liquidy star system very early on?
Yeah, certainly. I think there were lots of bodies that, right, we can look at the carbonaceous chondrites and we can say, hey, there were a lot of aqueous environments in the early solar system. Now, your view of the early solar system sort of depends a little bit of what you focus your attention on, right? The dynamicists or the people who study impacts may have a much more violent picture in their head of the early solar system of objects colliding and crashing together. And so you may think, well, okay, so all I mean by that is that your vision of the important geological processes may be skewed by whatever you think the relative importance of these early processes are. And they certainly factor into how stable the environment is, right? If you get catastrophically destroyed by an impact, that may not be very helpful for developing abiogenesis. But yeah, so for the bodies that are able to maintain these aqueous environments with the right ingredients, absolutely. I think there's many potential objects that could have had these environments. And even if, right, the time is a big component, there are likely many more objects in the outer solar system that also had sufficient time, right? All of these icy moons. Right, what kind of makes Ceres special is it's the closest one to us, right? The other outer solar system icy moons are much farther away. But all of these objects could have had the right aqueous environments early on and then maintained them for quite some time. Right, when we talk about the conditions for abiogenesis, again, they're not well known.
Something conspicuous. Something very conspicuous is that, Ceres seems to have a lot more water than we once thought it did. And we still have the mystery of what gave this planet its oceans. Its original water's gone, and it had to accumulate it after it cooled. And here we find that there seems to be a lot more water in the asteroid belt than what we initially thought. Do you think that was the delivery system of Earth's oceans? And could that delivery system, say a Ceres-sized object hits the Earth during the late heavy bombardment, something huge, and deposits water, but could it also have deposited life?
Yeah, I think this hypothesis has been going around for quite some time. And there's been various studies that look at, how did Earth get its water? How was it delivered? I wish I had the numbers off the top of my head of how much water Earth contains versus how much water, Ceres contains per volume. It's quite different. We think Ceres has, order of magnitude more water by mass. So, you could work backwards and figure out, how many Ceres-sized objects what portion of mass of Ceres would you need to deliver the water to Earth? There's also been studies of isotopes that look at, here's the isotopic measurements we have of various water-rich materials and then comparing them to the isotopes here on Earth. So this is a big area of research. Now, again, it's tough to know. We don't know the conditions for abiogenesis. Now, what I will say is if we found out, if we visited Ceres, if we figured out what its aqueous environment is like under the subsurface, if we could look at samples that tell us about that salty brine layer within Ceres, and we find, there is no evidence for life here. If we're able to say, hey, this environment was around for a billion years, salty water, sitting there with organics, and nothing. Well, obviously that means something wasn't right. Something was missing. Some condition for abiogenesis was not met, right? So you can sort of work the problem from two different angles. You can look at Earth and try to work backwards, figure out, here's life on Earth. How did it get here? We can look at life, how complicated it is, and try to figure out what set of conditions allowed life to form on Earth. Or we can go the other way around. We can go to places like Ceres and we can look at the ingredients that are available and figure out, well, if life isn't there, what's missing? So you can kind of see we can attack the problem from two different angles. And so, of course, this hypothesis of also, well, if life arose on one place or the other, could it have been transferred? I think that hypothesis has been around for quite some time. It's also fascinating But again, we have no constraints on it. We can speculate, but it's tough to tell.
Yeah, and it also goes both ways. So you get your mission sample return, you go to Ceres, you bring something back, and you find something that has the DNA of Earth, where it was transported from here to there. You know, there is so many options. Or you find something and you're like, well, this is the wrong chirality for Earth. This is definitely unique. But then you got to ask the question: did it form in that asteroid, or did it form somewhere else in the sun's birth cluster?
Right.
So I don't know if we could ever constrain, because that information is mostly long gone. So I don't know if we could ever constrain abiogenesis if it shows up that it first appears on an asteroid, because is it really from that asteroid, or was that asteroid just hospitable to it?
Right. I mean, and that's why it's going to be really hard to convince everyone that if we actually do discover microbes, we're going to have to rule out a lot of things first, right? You know, is it contamination? Was it delivered from Earth? You know, it is funny to think about, but we often think about life, panspermia, traveling from somewhere else and arriving on Earth, and that's the origin of life on Earth. But right now, as we know life, it would be easier for life, the life we know on Earth could be transferred to another body in the solar system if it were to arrive at a habitable environment. And so there have been studies saying, you know, just based on the lifespan of Earth, the duration of time that life has existed on the surface of Earth, the history of impacts on Earth, could life have moved from Earth to somewhere else in the solar system throughout its life? Obviously, we don't see life anywhere on the or anywhere else in the solar system yet. So there's no evidence that that process occurred. But it absolutely does go both ways, and it's fascinating to think about.
Now, Clay, you know, we looked at the asteroid Ryugu. JAXA went out there and got samples, and it shows the same evidence of the action of water. And Ryugu is probably a fragment of something that was much larger. And Ceres, probably not, as we were discussing. Is it interesting for you as a scientist to compare the two? In other words, you know, what does Ryugu look like versus Ceres?
Yeah, definitely. So, right, again, what I want to think about, what I try to break things down into are the processes, the geological processes that are occurring. Right, it's easy to get mired down in the details of classes of objects, classes of meteorites, the different types of compositions, different types of bodies, the difference between an icy moon, a dwarf planet, and an asteroid, a rubble pile. But it's all just material that's being acted upon by physics and chemistry. That material in, you know, Bennu and Ryugu, it looks like carbonaceous chondrite material. It's material that experienced aqueous alteration on some parent body before being disrupted and becoming a parent body, and becoming a rubble pile. I'm sorry, it was aqueously altered on their parent bodies. Right, what makes Ceres special is it's removing one more of those steps, whereas the material on Bennu and Ryugu has been broken up, taken from its parent body, reformed into a rubble pile. Ceres does not appear to be that. It appears to be leftover planetesimal. So it's a great lab for studying those parent body processes that otherwise have been lost in these collisionally evolved asteroids.
Do you think that we might have a clue here that the conditions for life to have arisen in the star system was dependent on the location of the asteroid belt? In other words, the presence of Jupiter sort of putting it just right there at the frost line, and you know, not too far out, not too close in. What's your sense of that question?
So I think one thing it's hard to capture without diagrams, so I'll do my best. But there's a bunch of parameters that are controlling the composition, the sizes, the number, and the eventual internal heating of these objects. So like, we want to constrain the interior environments of these objects. We want to know what if they had these habitable environments that were lasting. What controls the object's size, its composition? Part of that is where it formed. So we think that in the early solar system, there was this water ice line, as you mentioned, right? Where inside of the water ice line, there's no water ice that's stable. All the water ice sublimates, vapor gets pushed out to the point in the protoplanetary disk where water ice is stable, where it can condense. And so objects that formed on the outside of the water ice line, lots of water ice objects. On the inside, not so much. Lots of active research here. It may or may not be as clear of a picture as that. But yeah, absolutely. So the objects where this water ice line are, there could be this bunching up of material. It could be more likely to get objects to form near that line. And they'd be forming with a lot of water ice. Well, that's good for objects like, for objects to form habitable aqueous environments, right? We now have rock and water ice. Once that melts, we now have aqueous environments in all these little objects. The second thing that then controls the eventual fate of these environments is when they formed. If they formed really early on, the objects is going to heat it's going to heat a lot more. The earlier it forms, the more short-lived radioisotopes it's going to have, and the hotter the interior is going to become. So these early forming objects are the ones that are going to form metal cores. They could be the source of metal meteorites that we find. Whereas the later forming ones, we're talking, the early forming ones are within the first million years of the solar system. The later forming ones, a few to maybe 4 million years after the formation of the first solid objects in the solar system. Those would have just enough heating to melt the water ice, but not enough to melt their interiors and become like volcanic worlds with metal cores. And so all these objects that are forming outer solar system, beyond the water ice line, and late enough that they don't completely melt their interiors, they're just going to be these aqueous environments for quite a long time. There's a lot more nuance as you go further out in the outer solar system. There's other ice lines. You can have different compositions. There also seems to be a dependence on how much organic matter, depending on where it forms in the solar system. So all of these things are changing this possible starting composition of these planetesimals, which are ultimately determining the ingredients and how habitable they could become later on.
Now, one conspicuous feature of Ceres is this. There's a basin, an old crater that actually shows the evidence of having interacted with melted water from the impact, perhaps. But it is roughly antipodal with a mountain on the other side of Ceres that appears to be linked to cryovolcanism. Do you think that it could be a situational thing where you really, to maintain that heat, you really need it to be hit by asteroids? And, you basically mentioned this with the shattering, and that gives you a way for the cryovolcanism. But go deeper into that.
Yeah, so I think what you're getting at here, right, so let's imagine the interior of Ceres. And let's first imagine it isn't all that warm inside the center. It's cold, any sort of water would be frozen. And you could imagine hitting the crust of Ceres with an object, and that impact generates heat. And in that impact, you melt some of the ice there. That is one potential explanation for evidence of these, the bright spots on Ceres, some of these evaporites. The other option is there is liquid water in Ceres, at least somewhat recently, in the past tens of millions of years. And that impact is creating fractures. It's weakening the crust, allowing the fluid to come to the surface. That's the option that's favored by current research. And a lot of that is because we believe Ceres' interior is warmer. And that's just a fundamental aspect of physics. If Ceres has a temperature on the only way Ceres can lose heat is by radiating it from the surface. There's no way for the interior to lose heat except for it to conduct upwards and out and emit as thermal radiation off of the surface. So the temperature inside Ceres can only really increase. I think of one day I'll come up with an analogy for some daily object to help illustrate the concept better. I can't think of anything off the top of my head. But sort of the temperature has to increase with depth. And so that means at some level, the temperatures are right for liquid water. It's a question of when and where. And we also know that the density structure of Ceres is such that it gets denser towards the interior. And again, that's consistent with a icier crust. So a crust it may not be pure ice, but it is icier near the surface than it is towards the interior of Ceres. So that's where we get these models of Ceres interior, where it's like an icy mix of ice and rock and dust near Ceres' surface, progressing into perhaps this liquid briny layer. It could also be liquid water in like the pore space of rocky material, and then more rock towards the center of Ceres. That's one possible interior structure model that fits with Ceres. And so, right, it's this having this liquid water that gives the possibility for things like cryovolcanism, where the water tries to escape. So yeah, I think those are the pictures to paint when thinking about these questions.
I think what interests me most about the cryovolcanism at Ceres is that has to be, as far as I'm aware, the closest object that does that.
Yeah,
I mean,
absolutely.
Sure, you see it out at Triton, you see it out in the outer solar system. And like I said, Triton was going crazy with it. But at the same time, Ceres is a lot closer, and there is evidence there of it. I think that's the closest object that can do that, right? Other than maybe...
Yeah, it absolutely is. That's another reason why, like, for example, Ceres is a high priority target for future NASA sample return missions, because the Planetary Science Decadal Survey that talks about what the goals of future space exploration should be, a Ceres sample return is a high priority potential mission because it is somewhat close to Earth. It's in the asteroid belt, much closer than these icy moons around Saturn and Jupiter. And so it gives us an opportunity to grab a piece, right? If this material is from a briny layer within Ceres, if it has something to do with fluid escaping from the interior, we have a chance of grabbing some of the remnants of that.
And understanding more about cryovolcanism on small bodies in the solar system without having to go to Triton.
Right.
Yes. That geologically, that's interesting in and of itself, because that's something that, we don't have that on Earth.
No,
not
not
like
at
that.
all. It's obviously the bodies that have these well-formed ice shells, right? Ice on the surface of Ceres is not actually stable. It's too close to the sun. So any ice is shielded by whatever regolith, rocky, infall material is covering it. And of course, Ceres has a heavily cratered surface, so it's an old surface. So we're not talking about, so there certainly isn't as active of cryovolcanic processes as we see in the outer solar system. So if you really wanted to study the cryovolcanism, the examples in the outer solar system provide much more clearer pictures of it. It's more of the fact that it is there appear to be cryovolcanic features on Ceres that just makes us so much more excited about its interior.
Definitely going up the list of interesting objects as of late. I'm hoping for another mission. I know that the ESA was thinking of going there, but I don't know if anything ever came of that. But future missions to Ceres, is there anything planned?
No, nothing on the books. But as I mentioned, it's a high priority target for future NASA missions. It's on the list of potential missions that can be proposed in the next NASA mission cycles. And right, the picture I really want to paint is that it's this object in the asteroid belt. It's relatively close to Earth. It's relatively easier to sample than some of the objects further out. And it is a snapshot of the interior processes that could be ubiquitous, forming aqueous environments all over our solar system, all over other solar systems throughout the universe. It's a snapshot of the processes that we really need to understand. And I think that's what makes it so exciting.
Yeah, and there's always the wild card. Sometimes Japan will just decide to go do it and go get a sample.
Oh, it's certainly someone I really hope, I'm not biased. I want to know what's there. I want a sample. I want to know, is there this briny environment that was potentially habitable? So however we get a sample, I'm fine with.
Oh, me too, for sure. My last question in regards to Ceres is this. So maybe there are pockets of that brine left, but I would imagine in the geologic future there won't be, and that it will just become a dead object. Do you think that there is a giant extinction event going on right now, a microbial extinction event in process on the asteroid Ceres?
That is quite the interesting thought, and I guess that's why you're the science fiction author, because that never crossed my mind. But yeah, if a body like Ceres could ever have a biogenesis, if it ever had that event that created a community of microorganisms, yep, they would all be going away now, or already had a few billion years ago. So that's maybe not the happiest story for the Syrian microbes, but yep, that's precisely what would happen as the environment became colder and there was less chemical energy for them to survive. I will say, and in some of my research, that the microbial community that you would be able to support with the amount of energy would have been quite small relative to communities on Earth. There are like seafloor vents on the ocean on our ocean seafloor here on Earth, and like one of those vent systems is about how much theoretically a briny environment in a Syrian seafloor could support.
All right, Doctor, thank you for joining us today on Ceres, but we still have unfinished business because we're going to do another episode on Mars, which we will record here in just a few minutes.
Well, thanks so much.
Event Horizon and my channel are now available as a podcast on Apple Podcasts, Spotify, and YouTube memberships. Early ad-free episodes, bonus episodes, and sleep-focused content. Sign up now by clicking the links below to your platform of choice.